very quickly, let's recap exactly where we were. We said, in order to understand how to design optical networks, as we're going to use optical network as an example to introduce the various mathematical tools, we need to know the devices. And the devices, making it very quick, are these ones. Transmitters, so basically lasers, fibers, we need to know a little bit of propagation in fibers, multiplexers, or more in general, optical switches, any optical element which is able to switch directly in the optical domain, which is what we're going to do today, an amplifier that we haven't covered also last time. Indeed, when we transfer information over a wavelength, imagine this red wavelength, when we get to the destination, we need a receiver, we need to detect the light and transform the light into electrons, and we need also a filter which says, okay, to this receiver, you're going to receive only the red light. So we're going to go through all these elements. We already went through fibers and transmitters. We've seen how the fiber is composed. We've seen what is the passing bandwidth of the fiber, where the attenuation is particularly low. And we have observed that the transmission, the propagation of light in the fiber is actually related to this phenomenon, total internal reflection. And we've seen that it's very easy to model mathematically this property, because we have this law, the Snell's law, which tells us under which condition we are indeed propagating light into a fiber. Basically, we need to find what is the angle at which this total reflection happens. And then we were applying twice. Today we're going to do hopefully some exercises on this topic. We're going to apply twice the Snell law here and here, where there are the two boundaries between materials. And we saw that if you go by a fiber, typically you're not going to get in the data sheet of the fiber this angle, the angle at which you have to get into the fiber in order to have total reflection, but you get another expression, which is this expression here, the root of this, the difference between the squares of the two refraction indexes, which is basically called numerical aperture. The bigger the numerical aperture, the bigger is this angle by which you can enter indeed the fiber. We saw that the distinction between core and cladding is not that obvious, in the sense that there is a gradual transition between the refraction index of the core and the cladding. We saw that based on the dimension of this core, you can have multi-mode or single mode transmission. We described what is a mode. We calculated how many modes you have while propagating in a fiber, and we saw that there are pros and cons associated to having single mode and multi-mode transmission. Then we said, okay, you are propagating in a fiber, you have various problems while you're propagating in a fiber. First of all, you have to consider attenuation. The power in the fiber decreases exponentially with the distance that you travel into the fiber, according to this expression that we're also going to use in some exercises today. But it's not just about attenuation. It's also about many other so-called impairments, propagation impairments, other problems other than attenuation. So typically dispersion, that can be intermodal, polarization mode, or chromatic dispersion. We described quickly what they are. We saw that based on dispersion, we can have different kinds of fiber that can eliminate or not the dispersion. And then other nonlinearities, typically nonlinear refraction, stimulated Raman scattering, stimulated Brillouin, four-way mixing. That's it for the fibers. Then we said, okay, into the fiber we have to insert some light. How do we produce light at a specific wavelength? Second problem that we have solved last time. It's pretty easy. The element is called laser. well, pretty easy. I wouldn't say it's pretty easy from a scientific point of view. It was pretty easy the way I presented it. So basically the laser, this light amplification by stimulated emission of radiation, we saw that is based on a pretty simple property. We saw that you can have it through a PN junction, the characteristics of the laser. On this part I spent a little bit more time, and I'm gonna spend some time also today, because we basically said that while comparing the quality of two lasers, two important elements, two important parameters that represent the quality of a laser are these things: the tuning range, how far you can go in the spectrum while tuning the laser. Okay, can you stay just in a little interval of wavelengths, or you can go far? And the tuning time, how long does it take to travel in the spectrum to get to the new frequency at which you want to transmit? And we saw that based on the technology that you use to tune the laser, you have typically a trade-off between tuning time and tuning range. Quicker tunable lasers that have lower tuning time typically have also smaller tuning range. So you cannot have both, which was what we saw here. If you have a mechanically tuned laser, then you have a huge tuning range because you're mechanically changing the dimension of the laser. But then you have also a relatively high tuning range. If you change the refraction index of the lasing material, and by that you tune the laser, so acousto-optic or electro-optic change of the lasing material, then the tuning time is very fast, because it's just the time needed for the electromagnetic wave to change the refraction index. You're going to see today for filters is exactly the same. So, exactly, this was the point at which we were last time. We were starting to talk about the other side of the system. Now you have transmitted, you go through the fiber, you receive, you filter first, and then you receive the signal. So, detection or reception of a signal is actually, again, quite intuitive. So the idea is that this, again, should come from other courses, not from my course. But basically, when you transmit information, you can either have direct detection or coherent detection. If you have direct detection, it means that you figure out the value of the bit based on the intensity of the signal that you receive. Direct detection. If I see intensity, it's 1. If I don't see signal intensity, it's 0. This is the most obvious modulation format. OOK, on, off key, or amplitude modulation. So in this case, it's quite easy to do direct detection in optical. What you have to do is somehow represented here. You have a PN junction in a stable state, meaning that even if the N side has a higher number of electrons and the P side has a higher number of gaps, if you don't perturb the system, you have a certain situation. When light hits over the PN junction, some electrons are going to jump from one side to the other, and so you're going to produce some intensity, some electrical intensity, some voltage. Okay? So every time light hits the PN junction, you can measure that there is some electricity on the PN junction. That's how you do direct detection. Pretty easy. Obviously here there is a huge world of physics behind it, but the principle is pretty obvious. The other way by which you can detect a signal, coherent detection, is not by the intensity of the signal, but by the phase. Exactly. So how do you detect the phase of the signal that you get? When you are working at frequencies like the optical frequencies, it's a pretty tough job because you have to detect the phase when your sine or cosine, whatever you're using, is extremely rapid, right? You're at the frequency of terahertz. So detecting the phase of a signal that varies so many times in a second, it's very complex. So what people do is the so-called coherent detection. I'm oversimplifying as usual in these hours, but basically what happens is you have a signal at a very high frequency arriving to your receiver. There you have another laser, which is called local oscillator, which produces a signal at a very similar frequencies. And you should know that when you combine two signals over a specific, here it's called beam combiner, over a specific material, when you combine two signals with similar frequency, what you obtain is a signal at a frequency which is the difference between the two signals. So here you have F1, here you have F2. You combine them, you get a signal at F1 minus F2. And at that level, you can more easily detect the phase. Coherent detection. Again, it's not my job to explain what is coherent detection, just to give you an idea. So what is used in reality? What are people using? Direct or coherent detection? Both. In the sense that up to 10 Gbps is something that you might still buy nowadays, maybe for metro application, for example. It was direct detection. Starting from 40, nowadays, I would say the state of the art is 100 gigabit per second. And the first products are appearing at 400 gigabit per second over each wavelength. Standardization of 1 terabit per second Ethernet is undergoing, so it's not that far away. So for all these very high bit rates, you use coherent detection. So both of them are actually happening in the network. Before having the receiver, you need to filter out the exact wavelength that you want. I don't know how clear was this from the previous lectures. Let me quickly recap. Different lasers at different lambdas or different frequencies, same thing. You arrive at destination, you have to distinguish, you have to demultiplex the signal, right? So basically it's as if I'm saying you need to have, if this is the spectrum, you need to have in front of each receiver, let's say these are the receivers, you need to have a filter. What is a filter? Is an element that, while receiving all the frequencies from the spectrum, it has a passing bandwidth which is only one frequency, right? This is a filter. Everything else is removed from the spectrum. So you need a filter at the destination, at the receiver side. Okay, typically all the wavelengths, when you get all the wavelengths, you say you have a wavelength comb. You know what is a comb, right? Peculiar. Okay, so a wavelength comb is the set of wavelengths that you receive. Out of the wavelength comb, you only need to select one spike of that wavelength comb, the one that you need. How you do that? You can do it easily in optical. There are two main technologies. One is called Etalon. If you are now working on the course of Professor Martinelli, he might call it not Etalon, but Fabry-Perot cavity. It's the same concept. A cavity is basically some material with two glasses, with two mirrors at the end. It's exactly the same as the laser that we've seen last time, right? It was a material that we call cavity, and then two mirrors at the sides. But now we are not irradiating anything, we are not producing any wavelength. We get wavelength, the wavelength come, as I said before. Right? You have the wavelength arriving, this mirror is semi-transparent, meaning that you can get in, but you cannot get out. So the various wavelengths getting into the Etalon start bouncing back and forth between the two mirrors. If you decide appropriately the distance between the two mirrors, some of these wavelengths, when bouncing back and forth, will interfere with themselves destructively, so they will disappear. Some of the wavelengths will interfere constructively, so they will build enough power to get out from the other mirror. Okay? So this mirror has to allow parts of the power to get out. So this is the basic concept of the Fabry-Perot cavity that you might see also with Professor Martin. I'm not completely sure there's a good reception on my side. So, okay, now I have to change at a certain point of time, I have to change the wavelength that I want to receive. So, as I said last time, you can tune a laser, now you can tune a filter. How do you tune this filter? You change the distance between these mirrors. If it's a mechanically tuned Etalon filter. And if I want to have a quicker filter, you irradiate with some acousto waves or some electro waves, you change the refraction index, you obtain the same result. So the concept is exactly the same that we have seen in the lasers. You see? This Fabry-Perot would be the mechanically tuned. Mechanically tuned, large tuning range, small tuning time. Acousto-optically, electro-optically tuned laser filters, smaller at least tuning range, but larger. Sorry, smaller tuning range, but on the other side also smaller tuning time, which is what I want. Questions? I'm not losing too much time here. The concept, the physical concept behind it is exactly the same thing. So as you can see, there are acousto-optically tunable filters, electro-optically tunable filters, and then the Etalon, which is the mechanically tunable filter. There are actually two other ways of building filters, which are pretty famous. And when I say famous, I mean magazine kind of famous. This one is the Mach-Zehnder interferometer. If you follow this experiment last year, which was very well advertised on the press, the experiment on detecting the gravitational waves. What was the tool that they used to detect the gravitational waves? Was an interferometer. Up to the fact that this paper on which they advertised the results of the interferometer has maybe 100 authors, because obviously it was a huge effort in terms of research. One of the authors, maybe you know, is actually working with us in the group of Professor Monti. Anyway, what's the basic idea of an interferometer? Let's forget about gravitational waves. That's obviously a little bit more difficult than what I'm saying now. So, how do you, if you have a set of wavelengths in input, how do you cancel one of these wavelengths? The Mach-Zehnder interferometer says, just split the light. So you're going to have a copy of the wavelengths here and a copy of the wavelengths here. and then decide what is the additional delay of this. They say this is the upper arm. Okay, there are two arms in an interferometer. The upper arm has an additional delay such that the signal on a certain wavelength that goes through this arm has an 180-degree delay in the phase. So basically, if you delay the signal of 180 degrees of exactly the amount of space needed to have an 180 degree in the phase of that signal, then when they recombine here, one of the two disappears. The two signals disappears because they are exactly counter phase. Okay? So let me say it again very quickly. Interferometer, what does it mean? I create interference where there is no interference. So how do I create this interference? I split the signal in two, and I have a length on the upper arm such that the signal on the upper arm recombines with the signal on the lower arm exactly in counter phase, 180 degrees difference. And so the signal disappears. You wanna remove a set of wavelengths, you need to have a set of Mach-Zehnders one after the other.
This delay would be important to a specific wavelength. I mean, as two signals are identical, if you're gonna destruct them at the same threshold, we destructing everything. I mean, all wavelengths, so we get nothing at the output.
Yeah, as I was saying, you have to choose the length of this arm for each wavelength that you wanna somehow remove. Okay, so if you need to remove 3 wavelengths, you will most likely, it's a little bit more complex than that, but in principle, you're going to have 3 different interferometers to cancel those 3 wavelengths. There's also a way to tune the interferometer by radiating this delay line here and changing the diffraction index, so you can somehow tune also the Mach-Zehnder interferometer. The fiber-Bragg grating is a bit complex to understand why it works in such a way, so just be aware that there is another kind of famous and applied filter in optical networks, which is called fiber-Bragg grating, which is based on the idea that in the core of the fiber you change periodically. At a certain point you have what they say a grating, a periodic change of the refraction index, but we're not going to get into the details of how it works. Okay, questions on the filters? Very simple, high-level description. Amplifiers, as I said, you use optical transmission because typically you want to travel long. But if you want to travel long, I anticipated the first lecture, after 80 kilometers, attenuation is too much. So you need to go back at a higher level of the signal. So you need amplification. Before I start with the technologies, again, I don't know if you've seen these things in previous courses or you will see more precisely in other courses. But when a signal is under stress and you want to send the signal farther away, typically you can perform what is called 3R regeneration. Okay, the operation of cleaning the signal and sending the signal farther away is called regeneration. Why 3R regeneration? Because indeed, regeneration contains 3 possible ways of improving the signal. Always same example, you have a beautiful pulse in transmission. It goes 80 kilometers. For sure, we know that the intensity of the pulse will decrease. This is due to attenuation. Right? So for this phenomenon, you need the first R. You need to increase again the power of the signal. This is called amplification. Which is something you can do, we will see now, you can do in the optical domain. Amplification can be done in the optical domain. The second R, though, it's another aspect of regeneration, which is called reshaping. What does it mean, reshaping? As I mentioned before, we used to have in transmission the perfect pulse, and then going through a medium that, as we have seen before, as four-wave mixing, stimulated brilliant scattering, nonlinear diffraction, etc., etc. Not only it gets attenuated, but it also gets modified in terms of shape. Okay? So if I amplify this signal, I'm gonna get a signal which is like that, not the signal that I wanted to have, right? Can we do reshaping of the signal in the optical domain? Unfortunately not. This is something we need to have mostly in the electronic domain. The third R is the retiming. Retiming is needed because when you send a pulse, or better said, when you send a series of pulse, you would expect that they keep their distance, but that's not necessarily the case. They might start perfectly at a perfect distance, but then while they travel, some of them they might go faster, some of them slower, so they lose their timing. So you need to resynchronize the signal. Again, it's something that you cannot do in optical. You have to do it if you want to do it in the electronic domain. Okay, this is exactly what is written here. Signal regeneration can be 1 R, 2 R, or 3 R, meaning reamplification, reshaping, retiming. Only 1 R, only amplification is what we're going to see today in the optical domain. So the system, I think I don't need to spend much time here, right? The system, we've seen it many times. You have, people call it the distance between the source to the destination node is called the link. The distance between two amplifiers, okay, is called the span. Okay? The link versus the span. So every time you arrive to an amplifier, you re-amplify, as I was showing here, you re-amplify the signal. I already somehow suggested the fact that there are other problems that cannot be solved, like shaping and reshaping and retiming. There's another reason according to which, unfortunately, we cannot really just have amplifiers, cascaded amplifiers, one after the other. We're doing very good, right? We have thousands of kilometers, system with thousands of kilometers distance, reach. But still, I mean, there's a physical limitation to the amount of amplifiers that you can have one after the other. And to explain this concept, let me go directly to this example here. Questions? So, Imagine you're starting from the sides of the system, you're right here, you have a certain signal with a certain intensity, okay? 2 milliwatt, whatever it is. And then the signal starts getting into the fiber, it decreases its value up to a certain point, which is the point where you have the amplifier, and then the amplifier amplifies the signal, you go back to the original power. And then you get again attenuated and re-amplified, attenuated, re-amplified. To some extent, the last amplifier, this one, is the one at the destination node, and it restores again the signal at exactly the same level as it was at the source, right? These two values might be exactly the same, no problem. What is the problem here? The problem is that every time we amplify the signal at each of these zigzags here, you don't only amplify the signal, you also amplify the noise which is brought together with the signal. So if this is the noise level is several tens of dBs below the signal. Okay, this is 1 milliwatt. This is maybe 1 nanowatt at the beginning of the system. Then every time you go through the optical amplifier, you amplify the signal, but you amplify also the original noise. So from 1 nanowatt, maybe here becomes 10 nanowatt, and then 100 nanowatt, and so on and so forth. After a certain cascade of amplifiers, the noise, as usual, this is the problem in communication systems, the noise becomes comparable with the signals. So basically you cannot cascade as many amplifiers as you want, because you have this kind of situation. Here I plot the OSNR, the optical signal to noise ratio, and I show that even if the signal stays constant, the OSNR decreases. Okay? So unfortunately, after a certain number of amplifiers, we cannot really go farther away. Questions? How do I compare two amplifiers? When do I choose one amplifier over another? I prefer an amplifier with higher gain. This is the first performance metric of an amplifier. The gain is the amount of additional power that the amplifier is able to give to the signal. I have a signal arriving with the power small p. I have my amplifier. In output, I have the power G multiplying P. G obviously is the gain. Okay? The ratio between the output power and the input power of the amplifier. Very simple. Little more tricky is the gain efficiency. Every time you amplify a signal, you need an amplifier, and you need to power the amplifier. You need to give some power to the amplifier to amplify the signal. Like the amplifier is not a passive element. The amplifier needs some electricity to be powered. So typically here you will have a certain value again of power. This is the pump. That's how it's called. Okay? So as we can see here, the gain efficiency is the ratio between the amount of dB that you gain. Okay? This is simply G expressed in dB. So let's call it gain efficiency is the ratio between G in dB and the power of the pump in milliwatt. Okay, this is the gain efficiency. Obviously, ideally, you want to spend as few electricity as possible to power the signal. Anyway, here we're not talking about large amount of energy. Okay, we're talking about milliwatts and so on. The problems of the energy efficiency of the telecommunication networks are others, not really amplified. gain bandwidth is intuitive, is the amount of bandwidth of the spectrum over which the amplifier works. Not necessarily amplifiers amplify all the spectrum of the fiber. Gain saturation, there's a value, let's call it GS, gain saturation, which is an upper bound, okay? A value of power above which you cannot amplify the signal, okay? So you're going to amplify the signal by G, by the gain, but up to a certain level. Beyond that certain level, you cannot go. Typically, you saturate. Polarization sensitivity is related to the fact that electromagnetic fields typically has two polarization, and the amplifier might work on higher intensity on a polarization with respect to the other, not very important. And then the ASE, the amplified spontaneous emission. I mentioned in the example before that you have this noise that increases every time you go through an amplifier. Not just this. It's not just the fact that the noise that you had directly at the beginning of your system gets amplified. Unfortunately, every time you go through an optical amplifier, the optical amplifier adds additional noise, which is called AZ. It's unavoidable, amplified spontaneous emission. Questions? How the
Yes, basically every 80 kilometers you need one of these stuff in the fiber. I mean, how big are they? How they are powered? How they?
Yes, that's exactly what we start doing now. Now I will show you two possible versions, two possible implementations of the amplifier: the SOA and the EDFA. So let's see the description, and then if you have questions, we keep going. So one possible implementation, which I'm describing again very fast because it's not really what you find in the field nowadays. It's more like a research element, is this semiconductor optical amplifier. It's basically the usual semiconductor PN junction. And then as for the receiver in direct detection, you get some photons here. They activate some electrons. You know that when you activate some electron, you produce new photons. If you irradiate this system, it will be the same principle of the laser. If you irradiate this system, other than the electrons, the photons that you get, you have other photons which are stimulated by the reception of the initial photons. And so you increase the power. This is in principle very efficient and very simple, especially. Unfortunately, it has a very small bandwidth and it doesn't have a big gain, typically. Limited gain. So in practice, it's not much used, this semiconductor optical amplifier. What is used is this erbium doped fiber amplifier, EDFA. This is big. This is big also commercially. That's what is actually sold. How does it work? You have your own fiber arriving with the signal, and then you insert through a coupler. We're gonna understand better what is a coupler later, but basically it's an element which allows two fibers to be joined. Okay. So you have a coupler which allows the second fiber to insert a different wavelength at much lower wavelengths. Okay, so the pump laser typically is below 600 nanometers. Okay, so what happens here? That we have two wavelengths. We have our wavelength and we have the other wavelength. So, not a big deal so far. Nothing is happening. Magic happens when you add a piece of fiber doped with erbium. This erbium basically interferes with this wavelength, the pump wavelength, and sends energy of the pump wavelength to your signal. You remember when I talked about stimulated Raman scattering? when I was talking about stimulated Raman scattering, I was saying sometimes if you have too much power inside the fiber, then there is interaction between the molecules of the fiber and the power of the signal, and you get scattering, you start scattering the power over all the wavelengths. You can use that principle, that same principle for good. You can choose your own wavelength to be scattered to some extent, and scatter that wavelength exactly at the same wavelength of the signal, such that the signal gets amplified. This EDFA was invented in the 80s, partly also in Pirelli in Milan, and it works pretty well. It has a gain which is not perfect, but it's pretty large on the fiber band, and it doesn't really need much power. Okay, here we're talking again about milliwatts. So answering the question, how big are these elements? These are very small elements, which do not need much power. That's why under sea you can use it. You put this element there with a big battery, and for 10 years it's gonna work. And then obviously at the end of this doped fiber, you have this filter which doesn't allow the wavelength, the pump wavelength, to go into the system, because that would be detrimental to the performance of the system.
Physically, I just get confused, like how that the lower wavelength amplify the original data.
So basically, as in this Raman scattering, is not exactly the same principle, it's very similar. The power of this pump wavelength, when interacting with the erbium molecules, creates power or scatters power at higher wavelengths. If you choose appropriately the pump wavelength according to your wavelength, you can amplify, you can move the power of your wavelength over this wavelength. Other questions? Again, you have semiconductor or EDFAs. These are the two main amplifiers. As you can see, the gain of the EDFA can be pretty large. The gain of the semiconductor amplifier is somehow limited. That's why EDFA is more popular. Okay. This somehow ends the devices, the single elements. But we said the network is not really just transmitting bits between source and a destination. It's more than that. It's deciding where the information goes. That's where networking comes in. And you are used to see networks like IP or Ethernet networks, where you have these elements typically represented like this. You want to send information from A to B to C. This is not a very large network, okay, but the concept is that you want to go from A to C, then the packet arrives here, somebody reads the packet, inside the packet you have an IP address, you know where to go. So how do you call this property? The property of giving one input, choosing the output. This is switching. To be precise, all these names have a meaning. Switching is the generic operation of associating one input to one output based on some knowledge, some header, some addressing, and so on. Switching is typically subdivided in routing and forwarding. Routing is the intelligent decision that you take. That's why the IP router is called router, because it takes an intelligent decision, right? it gets the packet, there's an header, it goes in the table with all the headers. I'm making it very, very simple. And with the destinations, it is an intelligent decision. You read the header, you decide the output. Forwarding is the hardware, it's like software versus hardware. Forwarding is the physical operation of interconnecting an input with an output. At a certain point, the router forwards, in the sense that the router decides routing and then sends the packet outside of the router, forwarding. Okay? So this is like the physical level operation, and this is like the logical operation of switching. It's complicated, no? Because every company would have its own interpretation of these terms. Typically, at layer 2, when you have an operation like this one at layer 2, you say it's a switch, Ethernet switch, SDH switch, ATM switch. Layer 2. At layer 3, they call it routers. You do the same thing. You read an header and you decide the output. Okay? But at layer 2, they call it switch. At layer 3, they call it routers. What's the difference? Branding. Marketing. Not really. There's no real specific definition. Anyway, this would be the reasoning behind these words: switching, routing, and forwarding. Routing or routing. So let's get a little bit.
But as far as I know, like the difference between a router and switch, that the router supports multi technologies and the switch support only one technology. Like the router can, you know what I mean, yeah.
Yeah, there are even other definitions according to the speed by which you do the lookup of the table. If you do the lookup of the table hardware, then it's switch. If you do the lookup of the table, then it's router. There are different definitions. Okay? I think this is a reasonable definition, but other companies might have different definitions. Let's not overthink about this. It's minor. Other questions? So let's talk about switching a little bit. So before showing you the evolution of optical switching from the splitter, which was the elementary optical switch, to the reconfigurable optical hadron multiplexer, which I'm not sure I'm going to cover today, which is the most advanced switch nowadays. There's the whole evolution of optical switching. But before I start, let me just give some definitions of switching. First definition, which I guess is very easy and intuitive. Switching can be electrical or optical. You can switch the packet expressed as bits, as electrons representing bits, or you can switch the wavelength itself. You can switch in the optical domain or in the electrical domain. Let's see an example to be clearer on what I'm saying. You have your system with the wavelengths arriving to the node. This is the node. Wavelengths arrive. You demultiplex the wavelengths. You have on each output a wavelength. Forget about this element for now. I'll explain it later. So here there's nothing. Okay? So you have 3 wavelengths. You arrive with your wavelengths to this electrical switch. You move. You translate your photons in electrons. You build your frame. You build your set of bits. You interpret the set of bits. You take a decision and you go out. Okay? This is electrical switches. You move the signal from optical to electronic. Typically, you reconstruct the bit string. You identify your packets or your frames, you take your decision, and then you go back in optical. That's optical switching. Electrical switching. Optical switching would be, forget about electrons, forget about the bits, I just have a wavelength. Is this wavelength red? If this wavelength is red, I send it here. If this wavelength is yellow, I send it somewhere else. So I just do switching based on the color of the wavelength. Optical switching. We talked about this the first lecture. If you do this, you pay 1,000 times less than that, right? This is very simple to do. You have a ray of light, you just have to send the ray of light somewhere. You just need a glass, a mirror. Here you need an IP router. You go to Cisco, you give them $1 million, and then they give you an IP router. Okay?
Professor, for optical core, which devices are you using? Something AWG or around to split the different lights?
This is exactly what we want to do now, right? We will see for the optical core, there's an evolution from the very simple to today is this element here. So hopefully now, in the next 30-40 minutes, we go through all these elements before making some exercise. So first comment. This is a little. It's very marginal with respect to the discussion that we're having. Anyway, what happens in reality when you have an electrical switch in a real system is that you first terminate what is called the long haul wavelength. People are going to use certain wavelengths to go very distant. You terminate, this E is not needed for any switching or for any routing. This electronic conversion is just needed for 3R. Okay, you've been through long distance, you need to do reamplification, reshaping, retiming. Okay, so this is just regeneration. And then you go on a different wavelength between here and here. People call this one long range wavelength and this short range wavelength. If you go in a data center, you will see that physically. You have the fibers arriving from outside. Then you have elements which are called transponders. The transponders do this. And then from the transponders to the router, you have another fiber working on another wavelength, a short range wavelength. So this is the reason why it's so strange, right? You have O, E, O, O, E, E, O, and so on and so forth. It seems like there's redundancy of optoelectronic conversion, but that's how it works. Actually, nowadays, people are doing this a lot in telco, in telecommunication application. This is still pretty popular in more data applications, like data centers.
First one was long haul or long haul.
This is long haul distance, long range wavelengths. These are short range wavelengths. So you have different wavelengths when you have to do 2 meters than when you have to do 200 kilometers. So that's why you have this strange element here. And this is very confusing. But that's actually what happens during the evolution to this level. Actually, people didn't really jump from electrical switching to optical switching. For a while, they did an intermediate operation for which they were doing optical switching, but not directly on the long distance wavelengths, like here. They were going on the short distance wavelengths, using the short distance wavelengths to do switching, and then going back to the long distance wavelength. People usually call this approach an opaque approach and this approach a transparent approach. Every time you go through electronics, they say that you're adding an opaque layer. You have to go back to the bits. Not very important. The important thing is that you see the difference between this approach and this approach. Optical versus electrical. And here you have a little discussion if you want to check. Packet switching versus circuit switching. I use exactly the same slides I used to use the exactly same slides in my bachelor course of computer networks. And for me, explaining these two slides, circuit switching and packet switching, takes about 20-25 minutes. And I don't feel like doing it again. So I'm gonna take 3 minutes to explain these two slides. But if you don't understand me, this is important. You know, sometimes I get questions. I don't have a very good background on networking. I can take this course. Mostly yes, but please, you have to know what's the difference between packet switching and circuit switching. You have to really understand it. Not just packet switching, you divide the information in packets, circuit switching, no. Yeah, that's like the first point. But there's more than that. Okay? So I'm gonna go fast on these two slides. If you're not familiar with what I'm saying, go check it on some books, go check it on the internet and try to understand the difference between these two paradigms. Anyway, the main difference between these two approaches is that in packet switching, the information is segmented in packet segments, frames, whatever. And then each of these segments is treated independently. It's sent into the network, and the network takes care of delivering the packet, typically thanks to some information contained in what is called the header of the packet. Okay? The packet has some payload and some header. In the header, there's all the information the intermediate nodes need in order to get to the destination. In circuit switching, what happens is the information is not segmented, but you identify a pipe from the source to the destination, which is reserved to that connection from the beginning to the end of the communication. When I was doing phone calls on grandma's phone at home, I was taking the phone, dialing the number. While dialing the number, there was some signaling going through the network and reserving me 64 kilobits per second just for me, from the initial moment in which I called to the final moment. Okay? So that capacity was always for me, for nobody else. In packet switching, there's no reservation of capacity. I divide the capacity in packets and the packets go to the network. What's the problem? The problem is that in packet networks, you don't know in advance if you will have enough capacity because you don't reserve it. So how do you solve the problem that there might be no capacity? These intermediate nodes have buffers. So if two nodes, if two elements want to use the same exit at the same moment, if two packets want to use the same exit at the same moment, one packet goes, one packet waits. So the real difference between circuit switching and packet switching is that in packet switching, we use a transfer paradigm which is called store and forward. You send the packet, you receive the packet, and then you wait until it's your turn, and then you go store, okay, get the information, and then forward. So as you can see, the packet arrives, then you wait a bit, you send, wait a bit, so on and so on. Big deal with this approach, you don't know how long you're going to wait. So this time is not predictable. So the amount of time that you use to transfer a packet into the network has to some extent a variance that you cannot avoid. In circuit switching, as I said, I dial my number, there are some signaling packets that will reserve a path for me. When I get the path, all this capacity is just for me till the end of the call. So what's the big difference again between packet and circuit switching? That in circuit switching, the delay between source and destination is fixed. It's the propagation delay between me and the destination. In packet switching, the delay is variable. Okay? I can keep talking about this thing forever. If you have problems with it, go look for the Kurosi, whatever book of computer network you might have used, and just refresh on this problem. This is important because we will see that IP networks or Ethernet networks are packet-based networks. They use packet switching. The optical network is a circuit-based network. So the concept is very different. And they actually coexist. Typically, you place IP over the optical network. Sometimes you read books that will use a different terminology for switching, which is logic versus relational. Basically, the point is relational is circuit switching, and logic is packet switching. It's one level of, it's one conceptual level, it's one level of abstraction above. I say that is a relational switch when it simply associates one input with one output. Anything that gets into this input goes from this output. It's a relational switch. Optical switches work like this. The IP router doesn't work like this. You arrive in this input, you choose the output according to the value that is inside the packet, right? So it's not the position of the packet that decides the output. It's the content of the packet which decides the output, right? So relational switch is a circuit switch. It's a switch in which the input is univocally associated to the output. Logical switch, there's no univoc relation. According to the content inside the data, you decide the output. Questions? So now that we have the basis of switching, we can see how you do switching in optical. It's difficult to do switching in optical, right? You don't have buffers. I already said it last time. How do you stop a photon? There's no way to stop a photon. You cannot store the photon. So let's see what we can do. Is it clear? You cannot stop a photon. It's part of light, it just goes. Always goes. Faster or slower, but it goes. And in fact, the only way to store a photon, people tried it in these 20 years to do it, is to have a, how you say, a ribbon of fiber of a known dimension. Whenever you have to store it, you send it to this, it's called fiber delay line. You send it there, it goes. Then after 1 millisecond, you still need storage, okay, you send it there. After 1 millisecond, you send it there. That's how a optical buffer would work. But going back to the question that has been asked before, imagine how big would be the buffer. No? You need a ribbon of fiber, and maybe you need 100 ribbons of fiber to have 100 elements in your buffer. It's really it doesn't work. Basically, it hasn't worked so far. So let's see what we can do. The most obvious thing that we can do is this one. I have a fiber with some wavelengths inside. I just split the fiber and I send the information on both sides. This is called a splitter. This is very common in networking applications. So this is your fiber, right? The cladding and the core. You just split. You have to be careful. In this moment, you have to be careful such that the splitting happens exactly in the middle of the core. Otherwise, you have losses. Actually, you cannot avoid completely the losses here, and in fact, you have insertion losses. Again, due to the fact that this procedure is very sensitive, you might lose some power. And you have return loss. When you arrive here, a little bit of the signal will go back. But in a general sense, the splitter works pretty well. You have a certain power, it gets divided by 2. You lose some little percentage of the signal, but most of the signal is perfectly divided by 2. If you consider the combiner used in the other direction, If you use the splitter in the other direction, you have a combiner, right? It's the same thing. Now the signal arrives this way and it goes in the same direction. Obviously, what do you have to be careful of here? Which constraints you have if you want to use a combiner?
To be in the same phase.
Can you really use the same wavelengths here and here? No, otherwise they clash, right? They will overlap. So, if you want to combine two WDM comms, there should be no overlaps between the wavelength of the comms. And then if you place a combiner followed by a coupler, what happens? You have a combiner. Let's say we have lambda 1 and lambda 2, followed by a splitter. What do I have in the output? What happens here?
You can add.
After the combiner, and then you split. Okay? This is called coupler. Okay? You have two different signals, you put them together on both the outputs. It is quite intuitive to realize that if I put iteratively couplers one close to the other, I can basically have a coupler as big as I want. See this example here. 16 by 16. I have 16 inputs from lambda 1 to lambda 16 here. Again, what's the constraint here? There should be no two wavelengths in input which are the same, otherwise they clash. And what do I get here? No, in terms of wavelengths. Which wavelength? If I have lambda 1, lambda 2, blah blah blah, lambda 16, what do I get here, for example?
All of them.
All of them. Everything. From lambda 1 to lambda 16. This is the first switching element which has been built in optical, and it's called also passive start. You see, you have, this is another case, 4 by 4. You have 4 inputs, lambda 1, lambda 2, 3, and 4, and in output you have a copy of all the inputs. What is, third time I say the same thing, what is the constraint in order to have this element working? There should be no two inputs with the same wavelength. Is it clear why? If I have lambda 1 and lambda 1 on fiber 1 and fiber 2, then here I'm gonna have clash, overlap of the two wavelengths, which I cannot, right? This is always true. Also in radio, you cannot have two frequencies used by the same antenna, right? Same in optical. You cannot use twice the same wavelength. Does it make sense, right? The wavelength that's been used cannot be used by somebody else. Questions? But this is still very basic, right? We can only have an element in which whatever gets in gets on all the outputs. Now I deleted the network. The network is the switching into the network is more intelligent. You have an input, you want to know exactly on which output you want to go. So we still need to build up on this concept after the break. So let's take a break for 15 minutes till 15 minutes.